In the last couple of videos, we started thinking about a way to relate the way that a distribution factorizes and its conditional independence properties with a certain sort of directed acyclic graph. And in this video, let's start to formalize this relationship. So first we're going to need a little bit of notation, and this is just going to be sort of reviewing some sort of standard notation for graphs. So to be a little more precise, a directed acyclic graph, we say a DAG, directed acyclic graph. I'm going to assume some basic graph theory terminology. I assume you know what vertices and edges and paths and so on are. So I'm not going to talk about that. You can look all that stuff up pretty easily. But just to be clear here, by directed, we mean that the edges are oriented or directed, as the name would suggest. You know, these are directed edges. And acyclic means that there are no directed cycles. And this second property, so this property of having no directed cycles is equivalent to saying that the vertices can be ordered such that vertex I points to vertex j, or is a parent of vertex j. That implies, if that is true, that implies that the number I is less than j. So this is equivalent to saying that there are no directed cycles. If it has an ordering such as this, then there are no directed cycles, and conversely, no directed cycles implies that it has such an ordering, and that's something that you could prove. It's probably not too difficult. And this is called, let's call this, if we have chosen such an ordering, let's call that an ordered DAG, an ordered directed acyclic graph. If it's been given such an ordering. Another sort of standard notation that's going to be useful in this context is is to use this to denote what's called the parents of vertex I. And the parents of vertex I are all those edges. So let's look at this graph. All those edges that are, let me draw a new one we'll draw a new little graph here. So let's say this is 1, 2, 3, and 4. And we'll have edges from 1 to 2 and 3, and edges from 2 to 4, and an edge from 3 to 4. So in this graph, for example, I'll just give an example. So the parents are, well, in general, the parents are those vertices which are neighbors of a given vertex, and they point to that vertex. So, for example, the parents of 4 in this graph, e.g., the parents of 4 are 2 and 3. 2 and 3. And the parents of vertex 2 is just vertex 1, and the parents of 1, it has no parents, so it's just the empty set, which we write as that. Okay, and one more notational remark that will be useful here. Let's use, so if we have a vector, x1, x2, up to xn, let's use this notation, x sub a, for a set A of indices, to denote the tuple of x's, xi, such that I is in that set A. For example, if A equals 2 and 3, so if we're thinking about this graph here, so x would be, so we would have x1, x2, x3, and x4, and xa is just the tuple x2, x3. Those x's for which I is in that set. And so the way we're going to use this is for where the parents are this set A. So like for this one, the parents, so x sub pa of 4x parents of 4 is just going to be x2, x3. Well, I guess that was just this case. Okay, now that we have those sort of notational conventions all set, we are ready for the definition. Definition. Given a vector x of random variables, x1 up to xn, distributed according to some probability distribution p, and let's assume that this is either a PMF or a PDF, and an ordered directed acyclic graph, an ordered DAG. So I'm using this convention here. We've chosen some ordering on our DAG that satisfies this property. And by the way, this property was satisfied for all those examples that we looked at earlier. That was the thing where I was using a strange convention of lower numbers to higher numbers going downhill. So given this and an ordered DAG, let's call it G on n vertices, we say that x respects G, or sometimes we say that the distribution P respects G if the distribution can be factored as, do I have room over here? Let me put it down here in case I run out of room. The joint distribution equals the product as I goes from 1 to n of the probability of xi times the probability of each of its parents taking a particular value. Well, taking those values. So this is the key sort of formula here. Remember before I mentioned that it all comes down to the factorization of the joint distribution, and for directed graphical models, this is the factorization that I was referring to. This definition formalizes that notion that we were sort of developing before of the relationship between a directed acyclic graph and a probability distribution, because for any probability distribution, it satisfies this for some directed acyclic graph. We'll see actually, if that's not clear to you, we'll see later, why that's the case. And for any graph, there are certain probability distributions which will satisfy, well, for any DAG, ordered DAG, there are certain probability distributions which satisfy this. Of course, it doesn't uniquely determine the probability distribution, but it determines some collection of probability distributions P that respect that graph. And they respect it in the way that we talked about before. So here, remember, so just to draw the connection, before each of these factors, so each of these factors in this product corresponds to a factor in this product. Factors in this product, so let's see, so before, when we wrote down these factors, like for this one, x4 given x2 and x3, we had x4, and in the graph here, the way that we wrote down this distribution was we wrote down this factor, x4 given x2 and x3, because 2 was a parent of 4 and 3 was a parent of 4. And that's exactly what this is doing. This is saying that we're going to put a factor for each node in the graph, for each vertex in the graph, in other words, for each random variable, and that factor will have the value for that random variable given the values of its parents. So this is exactly what we were doing. Oh, and I should say this is, for any values x1 to xn that these random variables could take. Okay, so an example, right? I mean, you could, if that's not clear to you, you could check that this is an example of, so any distribution which satisfies this factorization for any x1 through x6 respects this graph, respects this DAG. So that's an example, and the other ones we did earlier were examples also. And now let me make a very important remark, something which was confusing to me when I was first learning this stuff. This does not imply any, let's say it this way, it does not imply that any particular variables, random variables, are conditionally dependent or dependent in general. Does not imply that. It only implies that certain random variables are conditionally independent, but it does not imply that they are necessarily dependent or conditionally dependent. So let me give you an example of that. So here's an example. If we have x1 to xn, let's just make it x1, x2, and x3. You can generalize it. And let's suppose these are independent. They are mutually independent. Well then, of course, their joint distribution, x1, x2, and x3, equals the product. Probability of x1, probability of x2, probability of x3. So, if we think about what this formula, this factorization in terms of this formula, or a graph, what would be a graph that this factorization would respect? If we took the graph, let's just say 1, 2, and 3, one node for each variable. And 1, we don't need to put any parents for 1, right? Because it's not conditioned on anything. So this graph, and the same for 2 and 3, we don't need to put any parents for 2 or any parents for 3. So if this was G, if this graph was G, then X, let's call X this vector, x1, x2, and x3. X respects this graph. If this is G here, I'll just put something so you know this is a graph. This is G. But also, switch colors, also X respects, we could also add some edges. We can add any edges we wanted. If we say we add this edge, well, we need it to still satisfy this, so we would need probability of x2 given x1, we would need this factor to be equal to this factor. We would need that to be equal to the probability of x2. And that's exactly what, since x1 and x2 are independent by assumption, then this is true. And so it also respects this graph.